In this module, we're going to talk about kinetics. And when we talk about kinetics, we are talking about how fast does a reaction go? And very interestingly, the data that we're able to collect about reactions and how fast they go, we can figure out the mechanism. That means something a little bit, not that different, but we're drawing different types of things when we do this in general chemistry. But kinetics and the way that some reactions are named and the mechanism that they go by, all absolutely related and will come up when you get to organic chemistry. So, for talking about how fast a reaction goes, I want to talk about how fast something else might go first, just to kind of put you in that mindset. So, if you're thinking about speed, right, if you were talking about the speed of a car, the speed of a skateboard, you could figure this out using change in distance over change in time, right? Delta x over delta t. The x is some kind of distance, right? Your end point minus your start point. You might have units of kilometers per second, for example. In chemical kinetics, we're going to use concentrations, how concentrations change over time. So, this first example reaction that we're going to look at is H2 gas plus I2 gas turning into 2HI. The rate of this reaction could be expressed as negative delta concentration of H2 divided by delta T. This is really negative sign and then big brackets, the concentration of H2 at time point 2 minus the concentration of H2 at time point 1 divided by time point 2 minus time point 1. The negative sign that's in here, it's there to account for the fact that the reactants are being used up. And when I give you the how to write the rate definition, that minus will be included in remembering how to put it all together. So it makes the rate of the reaction positive. So just like you would say that you're going 50 miles an hour, but you would not say that you were going negative 50 miles an hour if you were driving in the other direction, we will not say that a reaction is moving at a negative rate. We'll say that it's moving at a positive rate and include a negative sign in cases where our concentrations are going down because they're reactants in that expression. So this is going to fall under the definition of rate. We use the definition of rate at a specific time. If you know the concentrations, you can find the rate for a reaction instantaneously, like at a specific time point. It's not possible to use this definition to predict what will happen in the future. So as the reaction runs, does it go faster? Does it go slower? Does it go the same? There's absolutely no information in the definition of rate or in the overall reaction that will help you figure that out. We're going to have to do it experimentally. So measuring the rate of reaction has to be done experimentally. This is most commonly done with spectroscopy. So this is something that you have encountered in lab if you're taking the lab class. And it is really just looking at how much color is present. And we have an equation that will relate that to the amount that is present. So for this example reaction that we started looking at, H2 is a colorless gas, HI is a colorless gas, but I2 is violet. So as this reaction goes, right, from reactants to products, I will start out with a lot of violet because I'll start out with a lot of reactant, and then the amount of violet will go down as the amount of I2 goes down. And so this violet color will go away. We could measure how much light is absorbed at the violet light wavelength um, well, if it appears violet, it's not going to absorb violet, but we'll measure for I2, and the amount that's absorbed is related to concentration through Beer-Lambert law. I'm not going to ask you to do any calculations with Beer-Lambert law, but just so you know what it is, A is the absorbance. So when you put your sample in a spectrometer, spectrophotometer, whichever term you want to use, it kicks out a value that tells you how much was absorbed, and then it shows you the wavelength it was absorbed at. Epsilon is a constant, so I2 would have an epsilon value. B is the path length, which is it's 1 centimeter for every spectrometer I have ever seen. At any case, it's a constant, and then the concentration. So this is just a direct relationship between absorbance and concentration. We can also define rate according to the other reactant. So I had the rate definition against H2, but I could also say that the rate is equal to negative delta concentration of I2 divided by delta T. The negative is there because it's a reactant. As my reaction proceeds, its concentration is going down. Or I could say that my rate is equal to plus 1/2 delta concentration of HI divided by delta T. So the plus, it's a product. It's being made as my reaction is going. I don't have to account for that. But every time I use up my reactants, I make 2 moles of HI. So the 1/2 here ensures that the value of the rate is always the same across, like regardless of what you define it against. So if you were just looking at how the concentrations change, that HI is going to appear twice as quickly as your I2 goes down, because you get 2 moles every time. So we put a corrective factor in front of it. Making this generic so that you can see what it looks like for a whole equation. This is for the generic equation, little a, big A plus little b, big B, turning into little c, big C plus little d, big D. So when I want you to write it this way, I will ask you to write the definition of rate for the reaction in reference to what a reactant. So the rate for the reaction, if it's a reactant, it's negative 1 over the coefficient, delta concentration of that reactant over delta T. So for A, negative 1 over little a, delta concentration of A over delta T. For B, negative 1 over little b, delta concentration of B, delta T. And for the products, still 1 over the coefficient, but they have plus signs. So this is based on the definition of rate, and we will have other ways to calculate rate. I will explicitly tell you what they're for as we get to them.